let's look at lesson 98. As I said, it's a somewhat short lesson. Actually, it is a short lesson. I tend to see a lot of AP multiple choice questions that focus around fundamental theorem of calculus part 2. And so that's what we're going to look at. So fundamental theorem of calculus part 1. You know it. You use it all the time. You just honestly probably don't think of it by that name. Okay, so fundamental theorem of calculus part 1. Suppose f is a continuous function on the closed interval from a to b. If capital F of x is the integral from c to x of f of t dt. Okay, looks familiar, looks similar, right? But they threw in an x and they threw in t's and c. Notice what it says. Since f is an antiderivative of f, the derivative of capital F equals little f. So the idea is saying, if they ask you to take the derivative of capital F of x, they're asking you to take the derivative of the integral from c to x of f of t dt. Well, keep in mind, and x is a variable. This is just going to end up being f of x. And I'll show you an example in a moment that'll kind of prove that to you. But the reason being because this c, when you take the derivative of a constant, will cease to exist. And so it'll just end up being whatever f of x is. So let's look at example 1, and I'll show it to you both ways, and hopefully that makes sense for you. So simplify. The derivative of the integral from 9 to x of t squared dt. Officially, by fundamental theorem of calculus part 2, we don't have to show any work. The derivative of this integral is just going to be f of x, which f of x is whatever our function is evaluated at x. So t squared evaluated at x is going to be x squared. Okay, so this is equal to x squared. And we know that by the fundamental theorem of calculus, part 2. Okay, so because it's the derivative of an integral, we get to ignore the bottom number, and we basically just put x in place of t, and it's x squared. Now, I'm going to show you how it actually works longhand, just to show you that it does work. Okay, so if we do this the long way, so the derivative with respect to x of the integral from 9 to x of t squared dt. Okay, well, forget the d dx for a moment. Let's focus on this part right here. What is the integral of t squared? One-third t cubed. Evaluated between x and 9. So if we evaluate it from x to 9, what's this going to be then? Plug in the x, and so 1/3 x cubed minus 1/3 9 cubed. I don't know what 9 cubed is, and then I don't know what 1/3 of it is. 9 times 9 is 81, times another 3. $243. Okay. X of t squared dt is equal to 1/3 t cubed evaluated from 9 to x, which is equal to 1/3 x cubed minus 243, right? Except what were we supposed to do with all of this? Take the derivative. So now, take the derivative of all that work we just did. So the derivative of 1/3 x cubed minus 243. What's the derivative of 1/3 x cubed? X squared minus the derivative of 243. 0. What just happened? We got the same answer, yes? We got this long way is using fundamental theorem of calculus part 1. This is working out the derivative using fundamental theorem of calculus part 1. The shortcut, when you have the derivative of an integral, and that top piece is a variable, and the bottom piece is a number, is that your answer is just going to be this function at that variable. So, work it out the long way using fundamental theorem of calculus part 1, or, based on what we know, give your final answer. Okay, got it? Okay, what about example 2? The derivative of the integral from x to 4 of sine t over t dt. And notice they put the qualification as long as x is greater than 0, and that is just so that it will exist. Thoughts on this one? Not quite. There's a catch. Okay, so his first instinct is to say sine x over x, but the slight catch is that in order for this to work, x has to be on top.
So it's got negative sign up front and then flip.
Yes. Okay, so remember that integral property where you can flip the boundaries and put a negative sign out front? Yes, that's essentially what needs to happen. That I can rewrite this as d dx of the negative of the integral from 4 to x of sine t over t. Okay, so remember putting a negative out front allows the boundaries to flip. And so now, if we were to work this out, we would end up with the sine x over x, except there now is a negative sign out front. So negative sine x over x. Now, major difference between the first example and this example. The first example I could work out using part 1. This example, you can't really work out using fundamental theorem of calculus part 1. We can't really integrate sine x over x. Unless, I'm trying to think, unless you could do integration by parts. I'm not sure if you could or not. I feel like you would come to a roadblock. So, thus, now the shortcut is important, isn't it? Because it definitely made this problem a lot easier. Okay. It did. It made the first problem easier too. I showed it longhand to prove it, to show you why it works essentially. Okay. What about example 3? The derivative of the integral from 17 to x of e to the negative t squared dt. Yep. X is on top. We have a number on bottom, right? You have to have a number on bottom for this to work. No tricks on this one. I know you guys are looking for them because there's a trick on the second one, but nope. This is just e to the negative x squared. And again, that is by fundamental theorem of calculus part 2. Okay. One more example, looking at the natural logarithm. And as we look at this, it asks us to differentiate the natural log of x if it's equal to the integral from 1 to x of natural log of t dt. So officially, it's asking me to differentiate natural log of x, which means it's asking me to do the derivative with respect to x, yes? Which means we're doing the derivative with respect to x of the integral of 1 to x natural log of t dt. That's not supposed to be the natural log of t dt there. Forgot about this typo. Until I wrote it and I was like, wait a minute, that's not making sense. In order for this to make sense, it's supposed to be 1 over t. Okay. There we go. So the derivative of the natural log of x. And so we're doing the derivative of the integral from 1 to x of 1 over t dt. Well, whichever side you look at, what is this going to equal? According to fundamental theorem of calculus part 2, the derivative of this integral from 1 to x is going to be it's 1 over t here. Substitute the x in, which makes it 1 over x. And again, that is by the fundamental theorem of calculus part 2. Okay? I have a couple of changes in the homework. 2 is going to become 9 from 77. And then we are skipping 10 and 18 altogether. And then on 15, it's skip 15C and D. So you're still doing 15A and B.